Have you ever thought about mashing two popular frameworks together, Chromium and Node.js? Well, apparently GitHub has. Welcome to the birth of Electron. I smell arbitrary code execution. Anyone else? Before jumping into the video, let me introduce a guest on this channel to help me out with today's episode.
Hey guys, I'm Sinister Matrix. While I've caught everyone's attention, I would like to give a huge shout out to my buddy Pwn for making this whole collaboration happen. The time that was spent researching and implementing our findings into this video was a blast. Anyways, enough of these long-winded introductions, let's get on with the main event.
Alright, so let's start with arbitrary code execution. What does that even mean? Well, arbitrary code execution is the ability to execute any code on a victim's computer. This is also known as remote code execution, or RCE, which basically means it lets an attacker run code remotely. Sounds cool, right? However, finding code execution on a modern-day desktop application through buffer overflows or format string vulnerabilities isn't a piece of cake. Usually there are a lot of constraints when it comes to exploiting or finding these vulnerabilities in the first place. But as modern desktop application development evolves, we see new frameworks appearing every day. Electron is one of them.
Electron, originally developed and maintained by GitHub, is an open source framework for building cross-platform desktop applications. Electron's functionality lies in the fact that it uses Chromium as its front-end component, whereas it uses Node.js for back-end support. This means that ultimately, even though it's considered a desktop application by users, it would be more appropriate to describe it as a web application that integrates directly with your desktop. Now consider this. Because it uses Chromium for client-side operations, that must mean that it's pretty easy to develop and write code for, right? Yes, in short, all of those wonderful web-oriented languages like JavaScript, HTML, and CSS all work in conjunction when trying to develop Electron applications.
Off the top, we might be able to think of a couple of different ways to exploit an application when a web framework meets Node runtime. It's pretty much like giving a web browser control over native operating system APIs. And suddenly, all the client-side vulnerabilities become a big deal. There are a lot of scenarios where things can go wrong, but in this video, we're only going to talk about remote code executions via cross-site scripting or simply XSS. If you find arbitrary JavaScript execution in the context of an Electron app, then you can pop up a calculator instead of an alert. This is all made possible because of access to Node runtime environment, which is enabled by default, or at least at the time of making this video, but it's likely that it's going to change soon. This feature is called Node integration and is there to assist many developers creating desktop applications which need direct access to operating system level APIs. Typically, many developers use Electron to port their web app into a native desktop application. But along the way, they forget a couple of things, like disabling Node integration. If it's just a web application and it doesn't require any OS level APIs, there's no point in having Node integration enabled. So now we know a bit about Electron and how Node integration can be risky in an insecure environment, we can actually start breaking some applications.
However, before jumping right in, we have one more thing to talk about: tooling. Before blindly chipping away at any application, we need some way to be able to debug it first, to try and understand its core functionality before finding some bugs. For static analysis, we can decompile the Electron application from its azar file to its source using the npm package azar, which is an archive format like tar. We can simply extract this file and read the source code of an application. Oftentimes the code is bundled or minified in a way, but it's not really readable at first glance. But after beautifying and removing any unnecessary code, it typically regains any lost readability. To do some dynamic analysis, we can use the Chromium developer tools and set up a proxy with Burp Suite. Many times the developer tools aren't enabled in production. However, since we have the decompiled source code, we can enable developer tools and simply rebuild the application. Alright, now that we have a handle on debugging, Let's see how XSS can be used to gain RCE in Electron applications. As we have learned, Electron exposes node functionality through their use of node integration. So basically, instead of a simple alert pop-up, we can call the exec function like this. Here we can require a child process which will load this JavaScript module as part of the node core. This module has some handy functions like exec or exec-sync to execute shell commands. Let's give this a quick try. Let's go ahead and put the payload in the input box and boom, we get MS Paint.
Now let's get down into real meat of today's episode. During our 2 days research on Electron, we stumbled across an interesting cloud-based service for storing and sharing undisclosed information. We'll just assume this information to be in message format. This service was hosted on both web application and subsequently a desktop application as well. There was also a separate domain for hosting all the public messages that people want to share with each other. Roughly after about 2 minutes of looking into the desktop application, we immediately find an RCE via XSS. Simply put, that it relied on the image tag with a simple on-error event handler. Inherently, this also affected the other domain which was used to share messages publicly. Contrary to belief, this doesn't mean that people visiting the domain within the Electron application are affected by RCE. This occurs because the desktop application cannot directly visit any link sent by the attacker. So for the next couple of hours, we attached the desktop application to the Burp suite and began analyzing the traffic. After a while, we eventually found some small vulnerabilities which, upon being chained together, could gain remote code execution just by visiting one of the shared messages in the browser. You heard it right, the browser. Since we also had access to the web application, we looked into that as well, and eventually found a way to create messages containing our previous exploit code and get our remote code execution. Let me just explain you guys how the entire process worked. First, when the user visits the shared message containing the malicious code, the XSS gets triggered. However, as the request originates from the browser, we can only have access to the victim's session through JavaScript. Now, in order to create another message containing the actual RCE or remote code execution payload, we need a few key pieces of information, like for example, the access token, client token, UID, and GUID. I can't go into details of how these values were actually being utilized by the application, but just remember that we need these 4 things. Simply enough, all these values were stored in the local storage, and they were easily accessible through JavaScript, except for one, GUID. Now to make our create message request, we need this value. We need to get our hands on this value. However, finding GUID was not simple. We had to go through all our proxy history multiple times in order to find ways to leak this value. Eventually, we found an endpoint which takes the cookie and spits out a bunch of user-related information, including GUID, in JSON format. It was basically an API. Great, we can finally read our value. However, there was one more small problem: same origin policy. The policy prevents us from making requests to random websites on the internet and be able to read all the data cross-origin. But there are ways to loosen the same origin policy and effectively bypass it altogether. One of them is CORS, or cross-origin resource sharing. If the server responds with the access control allow origin header set to our domain, then the browser lets our domain read data cross-origin. However, in order to get the allow access control origin header in the response, the server should know the origin or where the request came from. In order to solve this issue, we can simply add an origin header in the HTTP request. The problem is that these types of requests are only allowed on its subdomains, but since request was coming from one of its subdomain, we can read the GUID value from the response without worrying about the same origin policy. After obtaining the 3 values from the local storage and bypassing same origin policy, to read data from the API, we had everything we need to create a message with RCE payload. Once we make a create message request, as expected, the web application will create a message with our RCE payload in it. But we're still inside a browser. How do we get the actual code execution? As it turns out, if you had the desktop application running in the background, it automatically reloads all the new messages using WebSockets and automatically trigger our RCE payload. Which means if the user had the application running in the background and visits a link in the browser, we get code execution. Alright, now let's see this in action. On the left side you can see the vulnerable application. Of course, this is a fake application, but it works similar to the real one. Now I don't need to touch this application in any way at all. All I need is this application to be running in the background. Now I'm going to set up my Netcat listener on port 4444 and I'm going to pull up my Google Chrome where I've logged into the web version of the application. And now if I visit the infected web page, I get code execution.